We'll be continuing on with dynamic programming. And as I mentioned, at times, in some courses, dynamic programming concepts are taught before we get into graphs, but I prefer to do it afterwards. And the reason is that it may be a little easier to understand some of the dynamic programming concepts if you have a few examples. Okay, so rather than telling you the theory, I would prefer to give you a whole bunch of examples, and then to be able to draw sort of broad conclusions as to what are the differences between the dynamic programming approach and the greedy approach. Okay, so that's the general methodology that I'm following. So today we'll try to complete the rod cutting problem, which we started off in the last lecture, and then we'll take another more complex example, which is that of the longest common subsequence. And this is also going to be a dynamic programming algorithm. So let's continue from where we left off in the last lecture. We broadly have already mentioned several times that there are a couple of properties that are there in dynamic programming algorithms, which is an optimal substructure, which is also present in greedy algorithms, but in particular, the overlapping subproblems is generally only found in dynamic programming algorithms. Okay, and as a result of the optimal substructure, you generally have a recursive solution. Okay, so that sort of goes hand in hand with an optimal substructure. So the rod cutting problem was defined in the last lecture, where we said that, let's say you have a rod of different lengths, and you have different prices for an uncut rod of a certain size. And these are not linear, as you can see. So if you're going from a 1 foot rod, let's say, to a 2 foot rod, instead of getting $2, you actually get a much higher price of $5 and so on. So you can see that there is some non-linearity in all of this. And it depends on the perhaps the supply and demand situation of rods of different length. So this is just a fictional perhaps example. And so the idea was that if you can take a particular rod, so let's say if you have a rod of size 10, then what is the maximum revenue that you can generate out of it if you look at possible different cuts in the rod? Okay, so you could break it up into 10 1-foot rods, so that would only give you a revenue of $10. But if you divide it up into 5 2-foot rods, then you can see that you can get 5 times 5, which is about $25. Okay, so this is a complex problem in general, and we said that. Let's see if it's out of the way. So if you have I minus 1 possible cuts, and at each point you can have either a cut or no cut, so there could be a possibility of 2 to the power n minus 1, because there can be n minus 1 possible cuts. So that's a pretty large space to be able to search. So it's an exponentially difficult problem. And so you need to obviously be able to find some solution which is non-exponential, preferably a geometric solution, either in order of n or order of n squared or something like that. And so we said, well, does it have the optimal substructure property? And so we saw that the optimal substructure property was there, and we were able to prove this in the last lecture. And I'm not going to go over that again, but hopefully that has not been lost after a week of holiday, or at least a few long weekend. So here is an example that we went through, and we said that, well, if you have a price table, and what you can do is you can construct an optimal revenue table. Okay, and the way you can do that is by starting off with the smallest rod size 1, and then you can build up sort of in a bottom-up approach. And you can say, well, what's the best revenue that you can get from a rod of size 2? And we saw that you can sort of build up on the previous solutions. And if you're looking for, let's say, a size of 7, if you have a rod of size 7, then how would you do that? Well, instead of looking up in the price table, which would be rather complex because the price table does not have the optimal solutions to the previous problems, to those previous smaller problems. What you could do is, as you've already built up the optimal revenue table solution, then you simply look up in the optimal revenue table solution. So essentially what we've done is we've saved all of this data, okay? And that again is a common property of all dynamic programming algorithms that we've already seen in graph algorithms, that we save past data and then we reuse them, okay? And this is something called memoization that we'll see soon, okay? So we saw that you could simply look up the solution in the optimal revenue table in some of these past, in the table that has already been saved. And so this is as far as we got in the last lecture. So let's take a look at formulating a recursive equation for this. So one way to solve this is the following. And I'm going to say, well, Rn is the optimal revenue. So this would be based on a maximum. And you'll see that this maximum comes up in dynamic programming algorithms, right? Because you don't really know which is the optimal solution. So you have to look through all the possible smaller solutions, okay? So here what we're saying is that, well, it could be, so let's say if you have a size 7, then it's possible that P7 is the optimal, okay? Or it's possible that one of the other sub-combinations are optimal. And so you could have a cut between 1 and 6, all right? So you look up the optimal solution for 1 and the optimal solution for 6. You compare that with P7, the price of 7, so 1 plus R6, or you could have a cut at the second point, which is R2 plus R5, and so on, and all the way up till Rn minus 1 plus R1, okay? So that's basically saying that we look at the rod and we say, well, is the current, if you don't make any cuts, is that going to give you the optimal revenue? Or if you make the cut at any one of the n minus 1 points, cutting points, and we calculate the optimal revenue for each one of them. So it's a recursive solution, okay? So when we're doing R5, for example, then you're looking up R5 over here, okay? Which is something that we already have. And R5 itself is based on an optimal solution of smaller revenues. So there is, as you can see, there is a couple of problems in this, okay? And the first one I've sort of highlighted over here, that there is some repetition. So you can see that R1 plus R6 is the same as R6 plus R1, okay? So that's one problem that we need to perhaps resolve. And the other problem could be that it is double recursive, okay? In other words, it's calling itself twice. So Rn is comprised of R2 plus R5, and then all the other combinations. So it becomes fairly complex. If you can see that just looking at one of these solutions is a double recursion, okay? You're calling yourself twice already, okay? And then you're doing this repetition n minus 1 times. So the complexity of this algorithm, you can see, is not very good, all right? So the first question is, can we write this in a slightly simpler way, okay? And any suggestions? How could we write this for example, first of all, how could we rewrite this to avoid the repetitions? There are some repetitions. You can see R1 plus R6 is the same as R6 plus R1. So how could we rewrite this equation to avoid the repetitions? Yes. Yeah. So it's not necessarily a triangle because it's not necessarily two-dimensional. You can think of it as one-dimensional. Okay. So in one-dimensional space, you can see that you don't have to go all the way from R1 plus R6 and then R2 plus R5. You can only go midway. You need only go midway. Okay. The second half of the table is simply repetitions. So you can remove some of these repetitions that way. All right, so you could cut this up into half and say, well, we're reducing it a little bit. That could avoid repetitions. So that was one solution. The other problem is that it is doubly recursive. All right, and the second question is perhaps a little bit more tricky. Can we convert this into a singly recursive equation? Now, in other words, it doesn't call itself twice. For example, Fibonacci series and so on, they also call themselves twice, right? But if you're doing a factorial, then you only call yourself once. So n factorial is simply n times n minus 1 factorial, okay? So can you convert this into a single recursive solution? It would still be recursive, but at least it won't be as bad as doubly recursive. So any thoughts on converting into a singly recursive equation? And that may not be so obvious, okay? So what we could do is the following. So we could say that, let's rewrite this as a max. And we say, well, every solution will have rods of either length 1 or length 2 or length 3 all the way up till n minus 1, right? Clearly, every solution will have one of those, right? So if every solution that you have has one of those rod pieces, then what we need to do is we can sort of decompose the problem and say, well, let's look at it as the left piece versus the right piece, okay? So we're going to look at the left piece, which is going to be a single rod, okay? And we're going to gradually increase its size from 1 to 2 to 3 to all the way up till n. And so this is that particular piece, is the left piece. And so since that has not been cut up, that's a single piece. So its revenue will simply be the price. Okay, you don't have to actually do an RI over here. It's an uncut piece, so it's going to be PI, the original price from up here. The other piece, which is decomposed the right side, can now be done in a recursive way. And we can say, well, the rest of the piece is n minus I. Okay, so we've taken size 1, done a recursion on n minus 1. Then we looked at possible solutions with uncut rod of size 2, and then done a recursion on n minus 2, okay, and so on. So hopefully you can see where this equation is coming in, and so it's avoiding the doubly recursion, and it doesn't have any repetitions as well. So this is a slight improvement and in the equation, and this is the equation that we're going to see if we can implement this, okay, and to convert that into an algorithm. So how would we convert this into an algorithm? Well, here is a solution, and we'll refer to this as a top-down solution, and most recursive solutions are top-down, okay? So for example, if you're doing a factorial of n, you say, what's the factorial of n? It's n times the factorial of n minus 1, all right? So you're starting with the top and you're going downwards. If you're saying Fibonacci of n, then you're saying Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. You're going downwards all the way till you get to the bottom, and then you have a solution, and then you go backwards, okay? So these are referred to as top-down solutions. And so in the top-down solution, we're going to implement this equation, and we're going to say, well, what is the maximum revenue that we can get from a rod of size n? And we give it the price table and the size n, okay? And we say, well, if n is equal to 0, well, the rod is of size 0, then obviously the revenue is 0. But if not, then we're going to start off by setting the initial revenue to be infinity, to be negative infinity, a really small number, okay? And then we'll start off the recursive part, and we'll start by making, as you saw, that we're basically doing a maximum of pi for I going from 1 till n. Okay, so we can start off with I is equal to 1 and go up till n. And so we're saying I is equal to 1, we're picking the current maximum value of the revenue, which is minus infinity, and we're going to look for the maximum. So as soon as you plug in minus infinity plus something which is positive, then it's going to replace the minus infinity. And then the first piece that we're going to look at is a rod of size 1. And then we're going to recurse on, try to figure out the optimal revenue for size n minus 1. Okay. And then we're going to look at an uncut rod of size 2, and then do a recursion of that. And every time we're trying to look at the previous best revenue that we've gotten. And if we're getting a better revenue, then we set the best revenue to be the maximum of these two. Okay. So that is a top-down solution. And if you think about the complexity of this, any ideas about the complexity of this? And does this look like a good solution? And is it really using the thought process that we had earlier? Okay, so we were earlier saying that, well, we've got a table and we're looking up in the table. The top-down solution doesn't seem to be utilizing that table, right? So it's simply doing a very simplistic recursion without utilizing the optimal revenue table. So clearly, it is not the optimal solution. Yes. Q and P. So P is the price that you get for an uncut rod of size I. Okay, and Q is the maximum revenue that you can achieve for a size of certain size. Okay, and that could be after you cut it up into different pieces. So P is an uncut. So let me go back again to this table. So these are the two tables. So this was the price table PI, which was the uncut. So if you have a length size 2, then we're not cutting it up into two small ones. Okay, and so the price is 5 for an uncut rod of size 2. Okay, so that's the price table. But the R and correspondingly the Q would be the optimal revenue that you can get after you can cut it up into small pieces. Is that clear? Yeah. Yeah, it would. So if you implemented it this way, I think this is what you're referring to, is that if you try to implement it in a doubly recursive way, then the solution would be the same. Yeah, so you're doing a recursion on both halves. You cut it up somewhere, and then you're doing a recursion on both sides. Okay, and what we're saying is that we can actually improve it. This is just another way of rewriting the same equation. Both will give you the same answer, but one will be a more complex algorithm versus the second one is a simpler algorithm. Okay. So here's the algorithm, and the question is, if it's not utilizing the revenue table, then what is the obvious problem with this recursive solution? And why is it not very good? Yes, Thomas. Yeah. So it's got an optimal substructure, but it's not utilizing the past results. Okay. So and it's got substructures which are being repeated. Okay, so not the optimal substructure, but you've got substructures which have similar solutions. So if you look at this, so this sort of makes it more clear. So if you're looking at, for example, a rod of size 4, so it's going to say, well, I'm going to use this equation. I'm going to say, well, so I'm going to say, I'm going to look at a repeat for smaller rods of n minus 1, and then n minus 2, so that's n minus 1, then n minus 2, then n minus 3, then n minus 4. Okay, so it's going to look at those 4 solutions, But when you call cut rod with n is equal to 3, it's going to look at a solution for 2, 1, and 0. Okay. And similarly, so you can see that there is a whole bunch of repetitions. Okay. So can somebody point out where are all the repetitions? So I hope it's obvious, but I just want to make sure that people are following. So can you see a whole portion of this graph, which sort of depicts the solution? It's in a graphical way. That a whole subsection of this is actually repetition. Yes. So if you look over here, then you can see that this is repetition, right? And similarly, this is also repetition over here, and this is a repetition over here. So essentially what you can see is that this whole thing over here is a repetition. Okay. So you could, all of this could be cut out if we were actually using the solution which we saw earlier, which was saving the data. And if you've already computed, let's say 2, okay, so when you're doing 4, you let's say compute 3, and then 2, and then 1, and then you save the solution. So when you next look at 0 or 1, you say, well, I've already computed the solution of 1, so I'm not going to recompute it. Okay. Similarly, once you've computed the solution of 2, and you need to recompute it, you're simply going to do a table lookup. Okay. So I hope that becomes clear. So we have to rewrite this algorithm so that it does a table lookup. Okay. And that is so almost a trivial extension of this. And here is the original problem. So this is cut rod, okay, which I'm copying over here. So this is the cut rod algorithm that we just saw. And now it looks a little bit more complex, but it really isn't. Okay. So the memoized cut rod. So memoized is not a misspelling of memorized. It comes from memo. Okay. So memo simply means that you're making, you're saving that data somewhere. So memoized top-down solution is the following. Okay. So it's going to initially start with taking the original price table, okay, and the size of the price table. And now we're going to have the revenue, the optimal revenue table, okay? And this goes back to this particular table that we had over here, which was the optimal revenue table, okay? And we're basically saying that now we're going to save all of that. So we'll remember the solution values in this R table. Now we've got the P table and the R table. So now we're basically doing a trade-off between time versus space. Okay, so we're using some more space, and hopefully it will cut down on the time considerably. And so we have our 0 to n. It's going to be a new array, and we're going to initialize all these values. So these will be the optimal revenue initially, and they're going to be set to be negative infinity, which is the smallest revenue that is possible. And then we're simply going to call the memoized cut rod auxiliary program, and that is going to have the same variable arguments, except that now we're going to pass it the revenue table as well. Okay, and now this is going to do a recursive call on itself, but a singular recursive call, as you can see. So this is essentially the same equation that we had over here. Okay, it's doing a max of the current maximum revenue that we have, and it's going to compare that with all the possible values for I going from 1 to n. All right, so which is what we did over here. And it's essentially the same, except there are a couple of differences. Now, every time we find an optimal solution, we save it in Rn. Okay, so once you've computed Q, you're going to set, you're going to save that in the optimal revenue table. And next time when you are calling it the value of n, you're going to first of all check whether you already have the optimal solution. Okay, if the optimal solution, which is here, is non-negative, which means it's not negative infinity, then you obviously have already computed it. And so we're simply going to return the value that you've already computed. Okay, So that was a slight modification of the simplistic recursive solution to make it memoized. Okay, in other words, using dynamic programming, right? So that's the basic idea: save past solutions and do recursion. And this is going to be a common theme, which we've already seen several times in graph algorithms for dynamic solutions. Now, what about the time complexity? Any thoughts on that? What do you think is the time complexity of this problem going to be? So it's doing for I is equal to 1 to n, okay? And then it's doing a recursive call as well, okay? So this may not be completely obvious, but it will give you theta of n squared solution, okay? And I'm not going to go over the proof of this. It can be worked out, but and the basic idea, the basic reasoning is that you're not actually working out on all of these solutions. Okay, if you did do that, then it comes out to be extremely bad. All right, and this can be proven as well. So if we say Tn is the number of calls to cut rod, and this is for the non-memoized solution, okay, then T of n is essentially an arithmetic series. Okay, so it comes out to be 2 to the power n, which is pretty bad, or as bad as you can get, besides going for something like n to the power n. But you can see a considerable improvement in that now, because we're saving the past solutions, we can simply solve this in polynomial time, and not just polynomial, but quadratic time. Okay, so I'm not going into detail of the proofs, but these can be worked out with a little bit of effort. Okay. So that was the memoized top-down solution. Now, one of the problems here is that there is a bit of a recursion overhead. Okay, so as you know that in recursion, you use up stack space and all of that, and it takes up more processing time. So can we improve this? So this is a memoized top-down solution, all right? And if you go back and think about how we actually solved over here, were we doing a top-down solution or was it different? So remember in last week, we started off and we did it differently over here. So was this a top-down approach? So we said, well, if you want to compute a size, the optimal revenue for a rod of size 7, did we start at 7 and go backwards, or did we do it differently? Think back to a week ago. Yes, yes, the back. Yes, the lady in the back. Yeah, yeah. So it was a bottom-up approach. Jane, if I'm not mistaken. Right? Sometimes my eyesight is not good, so sorry for that. So this was not a top-down approach, it was a bottom-up approach. And can sort of somebody try to explain why one would be better than the other? Somebody else other than Jane. Yes. Right. So if you know the order in which you need to solve the problem, and if you're going bottom up, and every time you're going bottom up, the problem that you need to solve, the equation comprises of problems which are smaller. Okay, then it makes sort of natural sense to go bottom up. Okay, because by going bottom up, got the table in the reverse direction, but you can imagine that we are going bottom up because this seems to be going top down, right? It's bottom up. But the bottom up approach is basically saying that we start with the smallest rod and then we pick the next rod size and so on. So we're incrementing the rod size, right? And so we're saying that when you need to compute the optimal solution for a rod of size 2, it depends on rod of size 1, okay? Solutions to problems of size 1. And similarly, the size for n comprises of solutions to optimal solutions to size of n minus 1 or smaller, okay? So if the solutions are smaller, then it makes sense to go bottom up. Okay, if you go in the bottom-up approach, then you're essentially building up your solutions as you go along, and every time you go to a bigger problem, you can just look up the previous solution. So that's essentially saying that do we need to now do a recursion? If you're going bottom up, do you think it's going to be a recursive solution? I mean, Kyle, you're saying no. Why not? You can just have a, sorry? Yeah, so you have the data in an array, and instead of doing a recursive solution, you are simply saying, well, I'm just going to look it up in the table, okay? So it's a non-recursive. So when you're going bottom up, you're actually coming up with a non-recursive solution, okay? And so that avoids the stack buildup as well. That is common with non-recursive solutions. So here's a solution which is a little better than the recursive solution, and that is the following, which is a bottom-up strategy. Okay, so in the bottom-up, it's fairly similar. Okay, we again have the same optimal solution. All right, so we're going to remember the previous optimal revenues, and we're going to start with a revenue for size 0. So we're starting off from the bottom up. So we're going to set the revenue for a rod of size 0 to be 0. That's kind of obvious. And then we're going to go from j is equal to 1 to n. Okay, so we're going bottom up, we're increasing the rod sizes from 1 to n. Okay, we set the initial optimal, we set the initial total revenue to be q, to be in minus infinity, which is saying that the optimal revenue that we have so far is negative infinity. And now we're going to do an I for a repetition from I is equal to 1 to j, because now we need to pick up the solutions from this set. Okay, so we're going to say, well, let's repeat for I is equal to 1 to j. So for the first case, when I is equal to 1, we're going to say, well, is P the price of 1 of a rod of size 1? How does that compare with a revenue of n minus 1? Okay, now because we're going bottom up, that indicates that we've already solved the solution for smaller solutions. So our n minus 1 is going to be a table lookup rather than a recursion. Okay, and so once we found the solution for Q, the optimal solution, we're going to save that in the revenue table, and we're going to return the entire table for whatever purpose this has. Okay, so that's the bottom-up strategy with memoization. Okay, because this is simply saving all the data into the table, so that's still memoization, and it does. What is important is that you need to make sure that you're solving it in the right order. Okay, so if you're going bottom up, then your solution comprises of smaller solutions. So R sub I j minus I is a smaller problem which has already been solved. So that's something that you need to be wary of. So this was the bottom-up strategy. What do you think is the time complexity on this? And this may be easier to see. Okay, because it's non-recursive and it's simply a table lookup. So what do you think, Jane? Yeah. Well, there is a problem where j is equal to 1 to n, and for I is equal to 1 to j. So you're still trying to compute this max. So it's not going to be linear. Okay. So we do. So in dynamic programming problems, you always not as compared to greedy solutions, in this case, you don't really know which is the optimal solution. So you actually have to compute all the possible solutions of smaller problems and look for repetitions. Those repetitions will have hopefully been saved, and then you're picking them up. But you still have to look through all the possible smaller problems. Okay, so it's not going to be linear because it is it has a nested loop. J is equal to 1 to n, so I is equal to 1 to j. So it's not completely obvious, but you can see that the number of iterations of loop 5 to 6 is going to be an arithmetic series. Okay, and so that gives you an order of or theta of n squared, which is basically n times n minus 1, something like that, divided by 2. So so the time complexity is again the same as in the previous case, which was the recursive, the memoized top-down solution also had the same time complexity. The only advantage over here is that you don't have recursion. Okay, and that can be a little bit of an advantage. So, so the conclusion so far is that if you have a dynamic programming, if you can perhaps take a problem and try to see if it's a dynamic programming problem, then you have to look for the original problems that we looked at, which was that does it have an optimal substructure? That's the first thing that you need to look at. You need to be able to prove that it has an optimal substructure, and then you have to look for overlapping subproblems. Okay, and we saw that both of them existed, and once you see that both of them exist, then you should hopefully be able to use a memoization. Okay, which is saving the data in tables. So whenever you have overlapping subproblems, then you need to be able to save these smaller problems and reuse that saved data. Okay, in terms of using more space in tables. So that's the general strategy, and it is a recursive solution because it is an optimal substructure. So this particular property results in a recursive solution. This property results in a memoized solution. Okay. So so that was one example of a dynamic of a problem which can be solved using dynamic programming, and this was perhaps a slightly easier problem than the one that we're about to start. Okay. So the next problem, which is perhaps about as complex as we're going to get, is what is referred to as the longest common subsequence problem. Okay, and if the rod cutting problem was a one-dimensional problem, this is going to be a two-dimensional problem. Okay, so a little bit more complex. But if you understood the basic concepts in the rod cutting and also in the earlier problems that we saw in graphs, you should be able to hopefully understand how the LCS problem is solved using dynamic programming. So where does this originate from? It basically originates from biological applications, and where you're trying to compare a sequence of two DNAs of two different organisms and trying to say, well, are these two organisms or these two species, are they similar to each other? And to what extent? All right. So you know that you have DNAs, okay, and DNA strands are basically comprised of 4 bases. So are there any persons over here who are double majors in biology as well? Yeah, a few of you guys. So you guys should know this, genome sequencing and so on. You hopefully studied that. Yes, no, somewhat. So you know that DNA strands basically comprise of these 4 bases, which is amazing. Okay, and every time I look at this, I'm amazed by the complexity of life. Essentially, the DNA is supposed to be the you can say the miracle of life. Okay, every living organism has a DNA. Essentially, every organism. Okay, maybe there are some exceptions, but primarily that differentiates between living versus non-living tissue. Okay, living versus non-living organisms. So, and DNA strands have this property that they're basically comprised of extremely long strand, right? The smallest strand that is found in some species is about 160,000, and the longest strand, which might comprise of multiple chromosomes, okay, can be as long as 43 billion. Okay, and human strands, which comprises of about 23 chromosomes, the largest is about 200 million, and these, when you add them together, is about 4 billion, is about 3 billion, 3.2 billion to be exact. Okay, so each of the human strands, all put together, will comprise of a combination of these 4 bases. Okay, so these are only 4 bases. These are amino acids. They stand for some complex amino acid names, which I can't remember, A, C, G, T for short. And what differentiates you between you and an amoeba, a single cell amoeba, is simply how your DNA strands differ from an amoeba or a chimpanzee, okay? Or your brother's, your sibling, okay? Both of you have different DNAs. And so if you want to see how similar or different you are as compared to humans and chimpanzees versus human and a starfish, then essentially what you need to do is to be able to compare the DNAs, okay, between the 2 species. And so the question is, how similar are X and Y? So here's a really small strand. So I'm comparing 2 strands, and they don't have to be the same. So here's a strand of size 7, and here's a strand of size 6. And we're saying, how similar is X to Y? Okay. And the question is, how do you define similarity? Okay. So can you come up with ways in which you would define similarity between X and Y? If you want to say, well, X and Y are very similar. So if, for example, if I had Y to be A, C, C, G, G, T, G, the only difference between these 2 being, let's say this is Y prime, then you would certainly say that X and Y prime are very similar, right? As compared to X and Y, which differ quite a bit. All right. So can you come up with your own definition of similarity? Can you think of ways to define how would you compare? You know, so you need to have a quantification of that. So you need to be able to quantify using a number to be able to say, well, is X and Y more similar, or is X and Y prime more similar? Okay, and I need to have some kind of a number, maybe an integer number, which can describe the similarity or difference between them. So any thoughts on how you could say how you could define a metric for the similarity of the 2 or the lack of similarity? Different ways that you could define. So, so if you think about X and Y prime, how would you say they're similar or different? Yes. Okay, so that's one way, is that you could simply align them. So that's what I've done over here. I hope you can read my handwriting. A little messy, but basically I've repeated everything over here, and I've changed one amino acid, one base. Okay, so the rest of the bases are exactly the same. And as has been suggested, that we align them together and we count how many differences there are. Okay, but if you compare A, X, and Y, then yeah, you can see that C and C match up over here. Okay, G also matches up, but then the lengths are also different. Okay, and you could have Y, for example, being just G and T. Okay, or Y could be GT and G double T and C. Okay, so if you look at Y and X, then there is no similarity, right? G versus A, C versus T, C versus T, and another C. But there is some similarity. And what is that similarity between, let's say, Y double prime and X? They're completely different lengths. If you line them up, there is no similarity, but there is one similarity, which is what? Yes? They both have substring GT, exactly. So if you think about G and T, okay, so GT is occurring, and C is also occurring, okay. So there are some substrings which are occurring, okay, but it's not exactly a substring, because you can also say, well, there could be some things in between. So you could have, for example, G A and T. Okay, so I'm now I'm calling this a Y triple prime. So let's say you have a GAT. Now there is no real match between Y triple prime and X, right? Because there is no substring which actually matches exactly. You can't say that Y triple prime is some substring of Y triple prime is a substring of X, right? Because now I've introduced A in the middle, so GT don't come together. Earlier, G and T were together, and you could see that this was common between X and Y double prime, but now I inserted something. So now you need to have a slightly more complex definition. Okay, and the definition that we're going to use is what are called subsequences. Okay, so by the way, so these are different ways that you could come up with a definition of similarity. So you could say one is a substring of the other. Okay, as you saw earlier, that GT, that a substring of Y double prime was actually a substring of X. Okay, but that becomes a little tricky, and that may not be true in a lot of cases. The other way that you could define is how many changes, and this is perhaps the first thought that came in, which is how many changes need to be made to convert one to the other. Okay, that is the first suggestion. And the third suggestion, which is actually the most powerful, and that is actually how that's an example of what we call the longest common subsequence. It's defined as follows. We find a third strand, and we call it Z, okay, in which the bases in Z appear in each of X and Y. Okay, so the bases in Z, appear in each of X and Y, which is where the common comes in. Okay, these bases must appear in the same order as well. Okay, but not necessarily consecutively. Okay, so that's quite a mouthful. So let's look at a few examples and try to understand what the LCS definition is. So first of all, let's think about subsequences. Okay, so what is a subsequence? So a subsequence of X would be all the subsequences shown as follows. So for example, in a subsequence, A could be present or not present, C could be present or not present, and in fact, both of them could be not present, or both of them could be present. Okay, but they have to be in the same order. Okay, so we're going to have that they must appear in the same order, but not necessarily consecutively. Okay, so in other words, you have for X being A and C, which is a size M is equal to 2. These are the possible subsequences. And now for M is equal to 3, can somebody tell me what are the possible subsequences for a slightly longer strand, which is A, C, and G? Jane. A, C, G. Okay, let's make it simpler. Do you think these, first of all, these are substrands of let's say X prime? So these are all, so let me first of all write that these are all subsequences of X prime as well. Why is that? Because in all of these, essentially, G is not present, right? So all we've done is we've taken these and we've said, well, these are all going to be present in these subsequences of X prime, because it's simply the case where G is not present. And so we're looking at the subsequences of AC and ACG. The subsequences of ACG also include the subsequences of AC, right? Now, what are we missing over here? So Jane, continue on from where you were. So can you put that in a simpler way? Yeah, exactly. So all you need to do is take this and add. So this is the case where G bar, where G is not present, right? Go back to your digital concepts. So this is the case where G is not present, and this is the combination where G is present. Okay, so you would have all of these situations. You would have A, C, and G, and all of these with G present. Okay, so you basically have the following subsequences. Okay, and then you have all of the same subsequences repeated, but now with G present. Okay, so now you can see that how can we actually figure out how many subsequences there are? And the question is, how many possible subsequences of X exist if X has length of size M? Okay, X's size is M. So how many possible, and you can hopefully see a pattern over here. Yes, sorry, to the power M, yeah. So hopefully everybody can see that we had, for this case, we had to the power 2, and then we had to the power 3, and then if you had M is larger, then it would simply be to the power M. Okay. So the space again is exponential, which is not good, right? So whenever you have these exponential solutions, then you know that you need to have a better solution, and a greedy solution or dynamic programming solution needs to be figured out. So now let's see where do we go from here. One way is that we try to do a brute force computation. Okay, so sorry, I haven't got to the LCS portion. So these are subsequences. Now let's talk about the longest common subsequence. Okay, when we say common, then clearly we're talking about two strands, X and Y, and now we're trying to see a common subsequence which is common to both X and Y, and there could be many of those, but we want to find the longest common subsequence. Okay, so these are some examples. So let's say X and Y, these are the same X and Y. I've just shown you different subsequences, which are, for example, you could start from here. So you could say, well, is A appearing in Y? Well, A is not appearing, so let's look at C. Is C appearing in Y? Well, it does appear, so there is a match over here. The next C is not matching, so is G matching? Yes, there is a match over here. The next G is not matching, and there's a T match over here, and then A is not matching. So this is one subsequence which is common to both, right? So CGT, C, G, and T is a common subsequence to both of them. Right, so that's one solution. Let's look at other ways of solving this. Now I could start from the bottom, and I could say, well, is G appearing over here in the top? So this is sort of like going this way, and now I'm going the opposite way, and I'm saying, well, is G appearing here? So G, yes, G is appearing here in X. Is T there? Yes, T is there, and C doesn't exist. And then you've got to have, well, and you can't go in the opposite, you can't cross over, okay? You can't use that. Why is that? Because the solution was that these bases must appear in the same order, but not necessarily consecutively, okay? So the bases have to be in the same order, but not necessarily consecutive. Now, you might say, well, what's the significance of the same order? Can somebody sort of try to intuitively think, why do you want them to be in the same order? Why is that perhaps important? And think not just of biological applications, but think of other applications as well. There are other applications of the LCS problem as well. So, and think of natural language processing. Has anybody studied NLP problems? You haven't done AI yet, so you probably haven't come across NLP. But natural language processing basically says that's what ChatGPT does, right? ChatGPT is basically a very powerful NLP algorithm. And basically what it does is, as you speak or as you type into ChatGPT, it looks at the words that you have already written, and it tries to predict the next word. Okay, that's all it's doing. is basically a very fancy prediction algorithm. And that's why you can't trust it. Okay. So remember that if you're thinking that any solution that's coming, that's coming out of ChatGPT is actually correct, well, no, it's a very simplistic solution. All it says is that it has this huge library, which is the entire universe, perhaps the entire Wikipedia, millions of books that's been trained upon. And all it's doing is saying, well, these are the words that have been put into me. What is the most likely next sequence of words? Okay. And it's basing that based on its past experience. And it's just combining those words. And sometimes they don't even make sense. Okay. So ChatGPT is not to be relied upon. And you'll see a lot of criticism of that as well. But some of the solutions are fantastic. And some of those don't make any sense. But the good thing is that it can learn. So if you say, well, the solution that you gave me is wrong, then it'll try to improve itself, which is something that you can't do with, just a Google search. So that's a sort of an aside going to AI. But the reason I'm asking you this is that it has some bearing on this issue that you want the basis to be in the same order. And if you're thinking about NLP, natural language processing, which is basically saying that if I'm saying something and you need to be able to predict what I'm going to say next, is the sequence in which I've said those things important, or can you jumble them up? So let's say I'm asking you a question. I need to make this up. Let's say I ask you, who are you? Okay. And if I change that into you are who, I mean, those I've jumbled them up. Okay. That doesn't make a lot of sense, right? And so you are who, the next predicted word could be very different from the next predicted word of who are you, right? So the sequence of the words is important. So similarly, in genome sciences, the sequence in which your DNA is being compared is important. Okay, so the sequence is important. That's basically what I was trying to point out, and that's why you don't have these crosses. Okay, so we're going to neglect these crosses. So we're looking for whether G occurred and then T occurred, and C can only occur in that particular sequence. Okay. So this is another solution, all right? But you can see that it's not so simple, okay? Because by jumping to T, we've perhaps neglected a better match, which was G matching with an earlier G, okay? So you can see that by selecting this particular solution, we have neglected a better solution, which was G matching with a G and a T match with a T. Okay, so you can see that you have different solutions, and it's not a trivial problem to be able to find the longest common subsequence. Okay, and in this case, the LCS, and there could be multiple LCS, which is the longest common subsequence. And in this case, you can see that this has a size of 3, this has a size of 3, this has a size of 2, and there are 2 LCSs. And they both have a size of 3. Okay, so that basically is the problem that we're trying to solve, to be able to find out a LCS, or maybe all of the LCSs, okay, or any valid LCS. But it has to be the longest common subsequence. That's our goal. Okay. So now let's see how we can use dynamic programming to solve this. So, so where do we start from? Where do we start from? So if I want to say, well, does dynamic programming, can DP offer a solution to the LCS problem? Where is our starting point? Yes, Scott. So in other words, you try to solve which of the two problems. Remember, there are two aspects which we need to look at all the time. There is the optimal substructure and the overlapping subproblems. Which of these are you identifying right now initially? Okay, so that's a good point that you're trying to say, well, does an overlapping subproblem exist? Okay, but before that, or even simultaneously, you could say, well, is the optimal substructure present? Okay, and it's not exactly clear to me as to your suggestion is that an optimal substructure and overlapping subproblem. Think about that again. You said that you think that there is an optimal solution, okay? And does that optimal solution comprise of smaller suboptimal solutions? So which one is it? Okay, but you've sort of, yeah, you're right, but you can break it out into two perhaps subparts, okay? First, if you can think of it as, does it have an optimal substructure? Okay, so let's try to identify whether it has an optimal substructure, and then if it has an optimal substructure, then we need to figure out whether we can find a recursive solution to the problem. Okay, then we need to look at if there's a recursive solution, then does that have overlapping subproblems? So you can think of breaking it down in a sequence of questions rather than attacking the problem all at once. Okay, so that's the thought process that I would suggest, and it's already been suggested that every time you try to figure out whether there's a DP problem there, then you try to break it up. Okay, first question, optimal substructure. Secondly, can you find a recursive solution to it? Okay, can you use memoization? Memoization would be used if there are overlapping subproblems. Okay, so break it up into at least 3 subcategories. Yes. Yeah. So that's sort of like another algorithm that we've already seen. Which algorithm are you referring to? With rod cutting as well. But the first type of rod cutting, where you divide up into 2 problems, right? So that was, if you think back to sorting, which of the algorithms in sorting does that remind you of? Yeah, so it's sort of like a divide and conquer problem. Okay, so you're dividing it up, but in the previous divide and conquer algorithms in sorting, did you have overlapping subproblems? You didn't have overlapping subproblems, right? But now the question is, can you find overlapping subproblems here? And if you can, then you can use memoization and to be able to save that data, and then you've got a dynamic a DP solution. Okay, so we didn't use in divide and conquer, we weren't able to use DP simply because there was no overlapping subproblems. Okay. So Kyle has given some good suggestions, and let's see if we can apply those, but we'll do it in a slightly more methodical manner, and we'll go step by step. And the first thing that we're going to take a look at is there an optimal substructure? Okay. Right, so before that, let's take a look at, can we do it in a brute force manner? Okay, and that's always a good idea. Okay, so figure out, well, do we even need to look for a DP problem? If the problem is, if you do it in a brute force manner, and if it's, if it's an order of n squared, then maybe you don't need to, put in so much thought into trying to find a DP solution. Okay, so and it's always a good fallback to say, well, what's the brute force complexity, and then try to see compared to your DP solution and see how much better have you done. So this is another example. So these are just words, then genome sequences. So horseback and snowflake. So I'm using the same approach. So I'm saying I'm starting with the top down. well, this is not, I won't call it a top-down, but just going from X to Y and saying, well, does H occur in Snowflake? No. Does O occur? Yes. If you have a match, R occurs? No. E occurs? Yes. So that's one match, and that's OE. Okay. But if you neglect E and you keep on going forward, you get a better match. Okay, because now you're getting A to A and K to K. Okay, so you're getting a longer subsequence. So you can see that you can't just pick the first solution that comes up. And similarly, if you go from Y to X, you could get S first, and then you could get A and then K and so on. So as you can see, in this case, there are again 3 subsequences, and 2 of them have size 3 and 1 of them has size 2. So the LCS are both Z2 and Z3. Okay. So now let's look at the brute force algorithm and see if we can figure out the complexity of this. All right. So first of all, let's generate all the possible subsequences of X. All right. And remember, this was to the power M. Okay. So what we're going to do is for every subsequence of X, for every subsequence, which is to the power M, check if it is a subsequence of Y. All right. So initially there are to the power M subsequences of X. And for that, we're going to, for every one of those, we are going to compare that to Y. So what's going to be the total complexity now? Just clearly to the power M. Okay, so you've got to the power M solutions over here. 1, 2, 3, 4 at least. And now what you're doing is you take the first solution and you compare it to Y. So how many comparisons would be required? So what's the total complexity? O of N comparisons, right? So this is of size N, okay? This is N and this is M. So there are N comparisons. Why is that? Because, for example, if you're doing AC, then you have to compare A to A, that's one comparison. Then you have to compare C with T, and then you have to compare C with C, okay? So there are, as you can see, you have to compare N times, okay? So the total number of comparisons is clearly N times to the power M. Or if you pick the smaller one first, so for example, if N is smaller, then you would probably do M times to the power N. You look at all the possible subsequences of Y rather than X because Y is smaller, okay? But in either case, it's a horrendous expression, okay? It's not just to the power N, but it also has M multiplied to it. So the brute force algorithm clearly is not going anywhere, all right? So now we look at the first problem, which is, can we find a property which says that there is optimal substructure or not? Okay. So think along the lines that perhaps Kyle started off with and say, well, how do we start off by, looking at an optimal substructure? What's been our thought process before? And I think Kyle sort of hinted that, and we saw that many times before. If you look at, we looked at the optimal substructure for the shortest MST, okay? Or we looked at for the shortest path, okay, or the minimum spanning tree. How did we start off trying to figure out whether an optimal substructure exists or not? Can somebody remind me? Not Kyle, somebody else. How do we go about figuring out an optimal substructure? And use your past examples, think back into your memories and figure out how we started off the optimal substructure. Yes. Yes, that was the proof. Okay. But before the proof, what was our initial hypothesis? Where did we start off with? So think about the shortest path, the shortest, the minimum spanning tree. Okay. And just recall, what do we do in the minimum spanning tree to be able to show that an optimal substructure exists? Not exactly. You made an initial assumption. and then you work backwards. There was an initial assumption in all the cases that we've done. So you need to think about these similarities in all of these algorithms, right? That's the whole beauty of this course, is that you find the patterns that exist between different algorithms. And if you can find those patterns and understand them, then if you get a new problem in real life, you can say, hey, I can apply that pattern over here, okay? But if you just memorize a particular algorithm, you're not really getting the whole advantage of this course. You need to be able to find the patterns, yes. Yes, so initially, what did we assume? That you have a minimum spanning tree. I've sort of said that. You start off by making an assumption, which I think Kyle can say it again. What did you just say a little while ago? Yeah, but you said something more important right at the beginning. You said that assume that we have an LCS. I think you started off by saying that, if I'm not mistaken. Okay, that was the first words. So basically what we're saying is that we're going to assume that we have a solution. Sort of going in the reverse, it's reverse engineering. Okay, so we're going to assume that we assume that we had a minimum spanning tree. We assume that we had an MST, or shortest path, and then we said, well, does sub problems, are those also optimal solutions? Okay, so we have an optimal solution. Can you show that the solution, that the smaller problems are also optimal solutions? So that's an important thing that you need to get out from this all of these examples. So we're going to assume that we have an LCS, and then we're going to work backwards. Okay, so let's see how are we going to do that. But before we can do that, we're going to make a few definitions. And we have a couple of minutes. I think I can get through the slide in a couple of minutes. So I'm going to define a very simple concept. I'm going to define the ith prefix of a particular string. Okay, so let's say you have a string X or Y. Okay, and X comprises of M characters and Y comprises of N characters. Then I can define the ith prefix simply by taking all of the first I characters. Okay, in other words, for example, if I say that the third prefix of A, B, C, D, E, F will simply be to take the first three letters, okay, A, B, C. And obviously then X is 0, the 0th prefix will be an empty sequence. And similarly for YJ, if you say YJ is the jth sequence, then the jth prefix, then the jth prefix will simply comprise of the characters Y1 through YJ, not leaving out any one of those. Okay, so that's a definition of an ith prefix, which will come across. So every time you see Y2 or you see X3, it will simply say, well, X3 means you've taken a larger sequence and you've just taken the first three characters of that sequence.